All righty. How's everybody doing this morning?
Good.
All right, cool. Okay, so today, as you probably know, is the last day of the semester before the final. So we're not going to cover any new material today, but we're going to review for the final. So the final exam will be next Tuesday, December 12th at 8 a.m. And everyone should meet in the lab rooms, okay? So, so what we're going to do today is that we'll review for the final. We just talked about when and where it will be. We'll talk about what's on it. It's two parts. It's a practical circuit and a multiple choice circuit. We'll go over the rules for the final, and then we will review the practical circuit part first. So we'll talk about how to do the math for that, and then how to actually build it on a breadboard and make the measurements. And then we'll go and do a brief review of the material that we've covered during the semester. And that will help to prepare you for the multiple choice section of the final. During the lab, we won't do a new lab today. We will do practice for the final. So that'll give you a chance to work on both parts, practice both parts of the final. You can also catch up on any work that you haven't turned in yet. And you can turn in any work up until the day of the final. So if you have a chance to do some today, you can turn that in today. If you're at home and you do some quizzes or stuff online, that's great too. You can keep on doing those up until the day of the final. And then the last thing, one of the most important things to do today is to check your grades. So your grades should be up to date at this point on the material that you have turned in. I already got one report that I've apparently lowered somebody's score inadvertently on several quizzes. So yeah, just want to keep you on your toes here. So, but the point is that I am human. I am prone to mistakes sometimes. So please check your grades. If you see something that looks a little bit off, let me know. I'm happy to fix it. And the sooner you find out and let me know about that, the better, because it'll just be a weight off your mind, and it'll be one less thing to worry about on the day of the final. Okay? So that's what we're going to be doing today. So any questions before we get going? All right. So let's start off. So again, the final is this Tuesday at 8 o'clock. This is an hour earlier than we normally meet. You should all meet in the lab rooms over there. Fred and Stephen will be here to start you off. I actually will not be here at the very beginning of the test. I will be here a little bit later, but Fred and Stephen will be there. We'll get you started. So 8 o'clock in your normal lab room, okay? So like I said, the test is broken into two sections. There's the practical section and the multiple choice section. So the practical section will be a circuit very much like we had on the midterm. It'll include 4 resistors, and you'll have to find the voltages and currents for those resistors, as well as the total resistance for the circuit. And we'll go over that in just a second. The multiple choice section will be just what it sounds like. It'll be multiple choice questions that cover all of the information that we've discussed throughout the semester. There are practice versions of both of these sections on Canvas. So I highly recommend that you check those out and do some practice. You can practice today in lab, and you can also practice when you're at home as well. Okay, so we'll go into those in a little bit more detail here in just a second. But let me talk about the rules here before we get started. So the rules for the test are very much like the rules for the midterm. So you can bring in one sheet of notes that has text written on it or printed on it on the front and the back. You can write whatever you want on there. You can bring in a calculator. You can bring in a pencil or a pen to do some scratch calculations. And we will provide scratch paper for you during the test, so you can do calculations. Other than that, books are not allowed during the test, and there's no use of cell phones allowed. You will use the computer to enter your data into Canvas, but other than that, you're not allowed to go to other websites or use other things on the computer. Okay. And the test is a personal effort, so you're not allowed to speak to your classmates during the test either. Okay. So each test will be individually generated for you. So every test will be slightly different numbers. So the circuit will include slightly different resistor values for each person, and the multiple choice section will include slightly different questions for each person. So those are the basic rules for the test. Any questions about that? Okay, so then let's start with a review of the actual circuit that we're going to be looking at on the exam. So the circuit is similar to the midterm in that it includes a power supply, so that'll be 12 volts like before, and it includes 4 resistors. But the resistors are in a slightly different configuration than they were on the midterm. So the resistors will look something like this. You might have a 500 ohm resistor here, for instance, 2000 ohm here, and then maybe a 10 kilo ohm here, and then 10 kilo ohm up there, say. Actually, let's make that a 4 kilo ohm. All right, so your circuit might look something like this. Again, each person will get their own resistor values, but this is the layout, the configuration that the resistors will be in. Okay, so let's go through, and we want to try to figure out the same things that we did for the midterm. So we want to know V total, R total, and then I total, and then we'll call this one R1, R2, R3, and R4, and we want to know VR1, VR2, so the voltages for each of the resistors, and then also the currents for each resistor. So we want to figure out what all of those are. So I'd like to do this 2 ways. So first of all, I'd like to go through it on the board and try and figure it out using math and circuit analysis. And then I'd like to also show it to you on the breadboard and show you how you can actually build the circuit and make measurements and figure out the values that way. Okay. So again, you are free to choose which method you use on the test. I would strongly recommend that you do both. But I'm not going to be, sitting there behind your desk, looking over your shoulder, going, "Ooh, ooh, ooh, that one didn't come from the breadboard. You can't use that." You can do however you like. Okay. So let's do the math first. So first of all, is this circuit a series circuit, a parallel circuit, or a series parallel circuit?
Series parallel.
Exactly, series parallel. So when we're looking at a series parallel circuit, we need to look at that circuit and see if we can find any elements that are in series or in parallel. And then we can use our formula to combine elements that are in series or parallel. And then we redraw the circuit, and then we look at it again and repeat that process until we're down to just a single resistor. All right? So let's do that. So when we're looking at this circuit, do we see any resistors that are in series or in parallel?
Yes.
Yeah. What do we see? So
R3 and R4?
yeah, let's look at R3 and R4. So R3 and R4 are in series because, remember the definition, what was the definition of series? That's right. So the end of one component is connected to the beginning of the next with nothing in between. And so that's what we have here. R3 is connected to R4 with nothing in between. Now, this circuit is a little bit tricky, and it throws a lot of people off. A lot of times, people look at this circuit and say, okay, well, I think R2 and R4 are in parallel. Let's start there. They look like they're in parallel because they're side by side. But remember, for components to actually be in parallel, they need to have their tops connected to each other and the bottoms connected to each other with nothing in between. So here, the bottom of these two components is connected together. That's good. But the top of the components is actually separated by this other resistor, R3. So even though R2 and R4 are next to each other, they're not actually in parallel. Okay? So that throws some people off. Also, sometimes it looks like R1 and R3 are in series because they're in a row like that. But again, in order to be in series, they actually can't have anything in between them. And this pair of resistors has R2 connected in the middle. So that doesn't really work either. So really, the only elements that are in series or parallel are R3 and R4 here, and like we said, they are in series. So let's find their equivalent resistance. So what formula do you use when you want to find a series resistance? Yeah, exactly. We just add them together. So we can find an equivalent resistor, and we'll call that R34, and that's just equal to R3 plus R4. So for this circuit, that would be 2,000 ohms plus 500 ohms. So that comes out to be 2,500 ohms. Does that make sense? All right. So then we can redraw this circuit and put in, instead of having R3 and R4 separate, we can combine them into this equivalent resistance, R34. So we still have our 12-volt power supply. R1 hasn't changed, so that's up here, that's still 4 kilo ohms. And R2 is the same. That's still 10 kilo ohms. But now we have R3 and R4 combined into a single equivalent resistance. We'll call that R34, and that's 2,500 ohms. Okay. So any questions about that? Okay. And then we repeat this process. So we look at this new circuit and we look for any resistors that are in series or parallel. So do we see anything? Yeah.
Yes.
What do we got?
25 and a 10 are in parallel.
That's right. That's right. So R2 and R34 are in parallel because the tops of the components are connected together with nothing in between, and same with the bottoms. Perfect. So we can find the equivalent resistance of those two. So we'll call that R234 because it combines all of those together. And what formula do we use when we have resistors in parallel?
The inverse.
Yeah, that inverse formula. So it's 1 over, and then 1 over each of the resistors. 1 over 10 kilo ohms plus 1 over 2.5 kilo ohms. All right. Now, if these had been the same value, I could have used that formula, but I could have used a simpler formula as well. What could I do if all of the resistors in parallel are the same value? Yeah.
You divide by the amount of how many you have that are similar. So if you have two
Right.
2500s, you do 2500 divided by 2.
Exactly. Exactly. So yeah. So that's perfect. So that would speed things up if they were all the same. But since we have different values here, we use this formula up here. So we can work this out. Now, remember, when we're using pretty much any formula in electronics, I find that the easiest thing to do is to convert all of the values to raw units before I actually do the math. So I don't leave it in kilo ohms or milliamps or, microwatts. I convert everything into plain units. So ohms, amps, volts, watts first. And then I do the math, because that way the answer comes out in plain units as well. Okay? Otherwise, the answer comes out and you don't really know what unit it's in. So let's convert everything to raw units here. So this is 1 over 1 over, and so 10 kilo ohms. How many ohms is that? 10,000, exactly. And 2.5 kilo ohms is?
2.5 thousand?
Yep, 2,500. Okay, so that'd be 1 over, so what's 1 over 10,000?
0.0001.
Okay, 0.0001, perfect. And what's 1 over 2,500?
0.0004.
Okay, 0.0004. So if we add those together, we get 1 over 0.0005. And if we divide that out, what does that give us?
2000.
2,000. All right. So that is our equivalent resistance, 2,000 ohms. So the equivalent resistance for these two resistors in parallel is 2,000 ohms. So we can redraw this circuit again. We've still got 4 kiloohms up there. And now we have an equivalent resistance here, which is 2 kiloohms. That'll be R2, 3, 4. This is R1. All right, so that's our new circuit. So we repeat this process again of looking for elements that are in series or in parallel. So do we see anything in series or parallel? Yeah, they're both in, these two resistors are in series because the end of one is connected to the beginning of the next with nothing in between. So, and we said that when we have resistors in series, we just add their resistances up to find the equivalent resistance. So we can redraw this circuit. And we have just a single resistor now. And that resistance is the sum of 4 kiloohms and 2 kiloohms. So that comes out to be 6 kiloohms. And that's the resistance for all of the resistors together. So that'll be R total. So up here we can write that R total is 6 kiloohms. So any questions about how we got that? Okay. So that's the equivalent resistance for the whole circuit. So then which of these items do you think we should attack next? What do you think we can look for?
Volts and current total.
Sure. Okay, so the voltage, do we have to do any math to find the total voltage?
No.
No. Because the total voltage just comes from the power supply there, so that's 12 volts. So do 12 volts. And then what about the current? How would we find the total current for this circuit? Ohm's law, exactly. So this brings us back to Ohm's law. This is one of the most important laws in electronics, probably the most important law. So remember, we write it like this. We got V, I, and R. So V stands for voltage, I for current, and R for resistance. And so in this case, we're trying to find the current. So we write down I equals, and we cover that up, and we see that it's V over R. So in this case, we're trying to find the total current. So we would use the total voltage and the total resistance. So the total voltage we said was 12 volts, and the total resistance was 6 kiloohms. So again, we want to convert everything to raw units before we do the math. So we convert that to 12 volts and 6,000 ohms. So what is 12 divided by 6,000?
2 million.
All right, perfect. So yeah, so it would be 0.002 amps, which is equal to 2 milliamps, like you said. All right, so that would be the total current for our circuit. So that's the amount of current that is going to be flowing through. It'll be the total current, remember, is the current that flows out of our power supply. So if we look over here, that means that we have 2 milliamps flowing out of the power supply there and flowing through that circuit. And since this circuit is equivalent to all the others, that means that we have 2 milliamps flowing out of the power supply in all the other circuits as well. So we can draw that over here. We've got 2 milliamps flowing out of that power supply. All right. So then, what is the next one of these variables that we can try and find here? Yeah.
So addition for R1, we can just put it as 2 milliamps, right?
That's exactly right. Yeah, we can find the current for R1, and we know that that's 2 milliamps because we have 2 milliamps flowing out of the power supply here, and the only path that it can take is through this resistor. So all of that current has to go through here. So we have to have 2 milliamps flowing through there. So, so we can write that down here. IR1 equals 2 milliamps.
I have a question. But
Yeah.
When we write the answers down for the actual final, if we write it as 0.002 amps or 2 milliamps, it won't matter.
It will matter because the test specifies which units you should use. So I believe that the currents are required to be in milliamps. So it'll show the unit on the test right next to the box where you're putting it in. So make sure that you put it in, you put in the correct value for that number of units. Yeah. Yep. So other questions about that? All right. Then what is the next thing that we could find over here? What's that?
VR1 because we know the current and the resistance.
Perfect. Yeah, exactly. So we can find VR1. And what law do we use to find that? Ohm's law. Perfect. All right. So we say that the current, again, we look at Ohm's law up here. We got V, I, and R. In this case, we're trying to find voltage. So we write down V equals, then we cover that up, we see that it's I times R. So then that would be 2 milliamps is the current, and then times the resistance, so that's 4 kilo ohms. So that's 0.002 amps times 4,000 ohms. So that comes out to be 8 volts. So that is the voltage for R1. 8 volts. And I like to draw these on my diagram as well, because it helps me keep track in my head of what's going on. Okay, so we've got 8 volts there. So now, what could we look at next? Which one of these things could we solve for next? It's getting a little trickier now.
I2.
I2.
We know V2 and
Okay, so well, how do we know V2 though?
because V2 is the same for the as the power supply.
Almost. So it kind of looks like it would be the same because it looks like it's in parallel, but we have this other resistor in between. So actually we don't get all 12 volts across R2.
Would it be 4 volts, Kirchhoff's law?
Yeah, that's perfect. So yeah, we can find that voltage using Kirchhoff's voltage law, like you said. So what does Kirchhoff's voltage law say?
If I remember correctly, going around that circuit would equal to 0.
That's right. So it says that the voltages around any loop in a circuit will add up to 0. So remember, a loop is a path that starts and ends at the same place. So we can look at power supply here. We know that that's 12 volts there. The top is positive, the bottom is negative, and then when we look at these resistors, whichever side is closer to the positive will have a positive voltage usually, and then the other side will have a negative voltage. Okay? So if we want to find voltage across R2, where could we draw our loop in order to do that?
Just going down to R1, R2, then back to the 12 volts.
Yeah, sure. So we could start right here and then go up and around and down and back there. So yeah, that's a great way to do it. And I like that because it only has this one voltage that we don't know. We know 12 volts here, we know 8 volts there. So we are only left with one voltage that we don't know. So that way we can figure out what that voltage is. Kirchhoff's voltage law holds for any loop around the circuit. So we could draw it anywhere we wanted. But if we drew it over here, say, we'd have 3 voltages that we don't know. And so we wouldn't be able to figure them all out like this. So this is a great way to do it. So let's do Kirchhoff's voltage law here. So we're starting at 0 volts. We go up by 12. So let me get a black marker so it's easier to see here. All right. So we're going up by 12 volts. So plus 12 volts. And then when we come to R1 here, there's an 8 volt difference across it, and we're going from high to low, like we're going downhill here. So we're going down by 8 volts. So minus 8 volts. And then we come to R2, and we're going downhill again there too. So minus VR2. And then we come back to where we started, and we said that when we go around that loop, all the voltages have to add up to 0. So all of these together have to equal 0 volts. So then we can just put our two known voltages together here. So 12 volts minus 8 volts, that gives us, yeah, perfect. So 4 volts, and then minus VR2 equals 0 volts. So that tells us that what is VR2 equal to? 4 volts, exactly. So that's 4 volts there. So across R2, we have 4 volts. So any questions about how we got that? Okay. All right. So that's the voltage for R2, is 4 volts there. So then what can we figure out next?
Current for R2.
Yeah, perfect. Current for R2. And what law do we use for that? Ohm's law, yeah. All right. So we say I equals, and then cover that up. We see it's V over R. So in this case, we're talking about R2. So voltage there is 4 volts. And then the resistance is 10 kiloohms. So that's 10,000 ohms. So what is 4 divided by 10,000? It should be 0.0004, right?
Yep.
So that would be 0.004 amps. So that's 0.4, yeah, 0.4 milliamps. So the current for R2 there is 0.4 milliamps. So we can draw this on our diagram there, 0.4 milliamps. So then, so what could we solve for next here?
ILP and
R3 and R4.
Yeah, yeah. And is there a law that we could use to find those currents?
Kirchhoff's current law for
Yeah,
R3.
perfect. Kirchhoff's current law. So, anybody remember what Kirchhoff's current law says?
Sum in, sum out, right, of the current to a node?
That's right. So yeah, so if we look at any node on the circuit, the sum of the currents flowing in equals the sum of the currents flowing out. So remember, a node is just a certain point that we pick on the circuit. So we can pick any point, and then we can look at the currents going in and going out. So in this case, it's convenient to pick a node that's right there at the junction between these three wires. So then we can look at the amount of current flowing in. So in this case, we have 2 milliamps flowing in from the right. So 2 milliamps, so the current flowing in has to equal the current flowing out. So flowing out, we have 0.4 milliamps. And also, the current that's flowing through R3 here, IR3. So 2 milliamps equals 0.4 milliamps plus IR3. So then, how much does IR3 equal? Yeah.
1.6.
Yeah, 1.6 milliamps. Perfect. So we have 1.6 milliamps flowing out that way. So kind of the intuitive way to think about this is that, remember, current is like the amount of electricity that's flowing through your circuit. So it's almost like water flowing through a pipe. So this would be like 2 gallons per minute flowing through this pipe here. We have 0.4 gallons per minute going down this way. So the rest of it, 1.6 gallons per minute, has to go that way. Okay? So that's what Kirchhoff's current law says. Another way to think about it is that it says that current doesn't build up at any one point in your circuit.
R4 is also 1.6.
That's right, exactly. So we have 1.6 milliamps flowing this way, and then all of it has to go through R4. It has no place else to go. So therefore, yeah, we have 1.6 milliamps flowing through R4 as well. So we can write that down for R3. We have 1.6 milliamps, and also for IR4. So, yeah.
Can you just explain one more time? How did you get the 1.6?
Yeah. So we used Kirchhoff's current law to find that. Kirchhoff's current law says that the current flowing into any node has to equal the current flowing out. So what we did is we picked a node right here where these three wires come together, and we looked at the amounts of current flowing in and the amounts of current flowing out. So the current flowing in was coming from the left here. So we had 2 milliamps flowing in. So we said that was the current flowing in, and that had to equal the current flowing out, according to Kirchhoff's current law. So the current flowing out, we had two paths where it could go. Some of it went down through R2, that was 0.4 milliamps, so we wrote that, plus this current that was flowing through R3, IR3 here. So we had 2 milliamps flowing in, 0.4 milliamps was flowing down, and the rest of it was flowing through R3. So IR3 is the difference between 2 milliamps and 0.4 milliamps, so that's 1.6 milliamps. Yeah.
And R3 and R4 share the same milliamps because they're in series?
Exactly. Yep. So once we knew R3, we could say that's the same for R4. Yep. So, yeah, other questions about that? Okay. And then, so the last two things that we have left are VR3 and VR4. So how could we find VR3?
Current transfer relations.
Yep, we could use Ohm's law again. So let's do that. So we say VR3 equals, we cover that up, we see that it's I times R. I3 times R3, so that is, so I3 we said is 1.6 milliamps. And then R3 is 2,000 ohms. So again, we would convert to raw units. So 1.6 milliamps would be 0.0016 amps times 2,000 ohms. So that comes out to be 3.2 volts. So that's the voltage across R3. Now there's a couple ways that we could figure out the voltage across R4. So what would be one of those ways? What's that?
Subtracting it from 12 volts.
Yeah, almost. So yeah, so we could use Kirchhoff's voltage law again. So yeah, so we could draw another loop around our circuit. So we could start here.
It's 3.2 minus 4, right? 4 minus 3.2. Oh, yeah.
Right, right. So so there's a couple of ways that we could draw the loop. So we could start here and go all the way around our circuit like this. Or we could, so if we do that, let's figure out how we would get the current or the voltage that way.
Divide 2 by 4.
Aha. So so these are all great suggestions, and we'll get there in just a second. So let's look at this outer loop first. So we're going up by 12 volts. So plus 12 volts first. So we go there, and then we go down by 8 volts. So minus 8, and then down by 3.2. And then down by VR4. And then we come back around to where we started. So that means that all of those together have to equal 0 volts. So therefore, we can combine all of these voltages that we know. So 12 minus 8 minus 3.2. Well, 12 minus 8 is 4 minus 3.2. That gives us 1.8 volts. And then minus VR4 equals 0 volts. So we could say that VR4 equals 1.8 volts. Okay? So that'll be one way to do it. Yeah.
Just 0.8.
Oh, I'm sorry. Thank you. Yeah, just right. Yeah, 4 minus 3 point, yeah. So 0.8 volts minus VR4 equals 0. VR4 equals 0.8 volts. Thank you. Yeah. So that would be one way to do it. Another way is we could use Kirchhoff's voltage law again, but this time we could draw the loop in a different way. So we could draw the loop over here. So we could go around this way. So if we did that, then we'd be starting here. We'd go up by 4 volts, so plus 4 volts, and then down by 3.2 there, so minus 3.2 volts, and then minus R4 equals 0 volts. So again, we combine what we know. So 4 minus 3.2 gives us 0.8 volts minus R4 equals 0. So then R4 equals 0.8 volts. Okay? So we get the same answer. We just use a slightly different technique to get there. Right? And then somebody mentioned one other technique, one other law that we could use. What would be another law that we could use to find the voltage for R4? It's my favorite one in the whole semester here. Yeah.
Just dividing?
Right? And what law is that? Ohm's law. That's right. That's right. All right. Yeah. So we could use Ohm's law again because we know the voltage. I'm sorry. We know the current and we know the resistance. So if we wanted to do it that way, we would say V equals I times R. So that would be, in this case, 1.6 milliamps times 500 ohms. So that's 0.0016 amps times 500. And that gives you 0.8 volts. So anyway you slice it, we come out with the same answer, which is 0.8 volts. So I guess the point I was trying to make here is that in electronics, there's often many different ways to get the right answer. So it's helpful to know lots of different options, and then you can pick the one that is easiest for you or works best in a particular situation. Yeah?
Can't you also just divide by 4 because 2,000 ohms and 5,000 ohms, it's a fourth of it, so you could just divide 3.2 by 4 and you'd also get 0.8.
So you could think of it as a voltage divider. So if you were thinking about it that way, you would have up here 2,000 ohms, and then down here 500 ohms, and you would know that you had 4 volts across the total. And so remember the way that the voltage dividers work is that you look at the fraction of the total resistance, and that's how much each one of these gets. So the total resistance would be 2,500 ohms here, and then the top would be 0.8 or 80% of that, so it would get 80% of the total voltage. So 80% of 4 volts would be 3.2, and then this would be 20% of the total resistance, so to get 20% of the total voltage, which would be 0.8. So so that would be another way to do it. So any questions about that circuit or how to do the math for that circuit?
So right there for volt 3, 1.6, how did we convert it to 0.0016?
So this is 1.6 milliamps. So to convert from milliamps to amps, what we do is we divide by 1,000. And one quick way to do that is to move the decimal point 3 places to the left.
Okay.
Yeah. Other questions? All right, cool. So then let me take a minute and show you a little bit how you could actually build this circuit on a breadboard and how you could make measurements of that circuit. Okay, so if you want to build the circuit on a breadboard, this would be one way to do it. So the red and black wires here on the left represent the power supply. So you would have the positive and negative leads from the power supply coming into your circuit here. And then you would have one resistor here at the top that's connected from your power supply over to the middle of the board. And then that would be R1. And then R2 comes down here from R1 to ground. Now I'm using this whole long row here along the bottom of the board as ground so that I can have lots of different holes where I can push those resistors in. And then R3 is across here at the top, and then R4 is over here on the right side. So this would be one way to build the circuit. There are many, many different ways that you could build it. You're free to do any way you like, but I try to make my circuits look kind of the same way that they look on the diagram, because that way it helps me keep things straight in my head. Okay? So this would be one way to build the circuit. And then once you have built the circuit, you want to actually make measurements and measure the voltages and the currents for this circuit. So actually the first thing that I would recommend, even before you build the circuit, is that you measure the resistance for each of your components. Because if you pick up a resistor and you think it's 1 kilo ohm, but it turns out to be 10 kilo ohms, and you forget to measure it, you build it into your circuit, you do all of your measurements, and you could get all the way through your test and get answers that are wildly different than the ones you calculated, because one of your components is much different, okay? And remember, it's easy to pick up a wrong component. Even if you open up the right drawer, pull out a resistor from that drawer, sometimes it could be wrong because somebody else put the wrong one in place. Yeah?
Having been in the lab for the last, how many weeks have we been in school?
Right.
4 or 5?
Yeah.
About 50% of the time that you pull out a resistor, it's going to be the incorrect one.
Yeah.
But the average is. How many have found that?
Definitely.
Okay. So measure these. What Jordan's saying is he's trying to help you guys out.
Yeah.
You're going to be all excited to take a test and want to grab things and put them in, but measure them. Take that extra 30 seconds. It doesn't take long.
Right.
It'll save you from being real frustrated.
Yeah, save you a lot of stress too. So, yeah. So let me go over how to measure a resistor. I know we've done it lots of times now, but we're reviewing, so let's just do it one more time here. So, what you can do is you take your meter and you put it into resistor measuring mode. So the unit for resistance is ohms. So if we look at the meter, this bottom left quadrant is the section where we measure ohms. And what do these little numbers on these different sections represent down here? Yeah, the maximum value that you can measure in that particular setting. So the first one down here is 200. So that means that in that setting you can measure up to 200 ohms. Okay? Ha! Oh, geez. I pulled a meter that's totally dead. Would you mind grabbing another one? Or,
Number one is the resistors. It'll be bad.
Yeah.
It'll be the meters.
yeah. So I should have checked that. But Yeah, the old, yeah. So, yeah, so while he's doing that, let me just point out a couple other things about the meter here. Sometimes the meters run out of battery, obviously. Sometimes, though, they can be low on battery without being totally dead. And if it's low on battery, it might give you questionable readings. So the way that you can tell if the meter is low on battery is that there's a little symbol on the meter that, that looks like a little car battery. And if you see that, it means that you have a low battery on that meter. Don't even fool around with it. Just give that to me or Fred. We'll get a new battery for it, and you just grab a new one, okay? There's plenty of meters back there, so just grab one that doesn't have the low battery, so you don't have to worry about that. The other thing is that sometimes the meter could be in maximum mode. So you might see a little indication at the bottom of the meter that says max. What that will do is that will show you the maximum value that your meter has measured since you turned it on, okay? So sometimes that could be helpful for some applications, but if you don't know what it is, it can really throw you off, okay? If your meter, you measure a 10 kilo ohm resistance, say, and then you try to measure a 1 kilo ohm resistance, and you're in max mode, it'll still show you 10 kilo ohms, all right? So you need to make sure it's not in max mode. So you would push that max button to get rid of that. Finally, the last thing I wanted to point out was that the meter has AC measurement mode and DC measurement mode, okay? So you want to make sure that you are on the correct mode when you're measuring your values. So in this class, all of these values, the voltages and currents that we've been talking about for this circuit, those are all DC values. So you want to make sure that your meter is in DC mode. So if it's in AC mode, it'll have a little indicator down at the bottom of the meter usually that says AC. Okay? If you see that, you want to switch out of that. You push this button one time, and that'll switch it out of AC mode and into DC mode. Thank you so much, Fred.
About two, just in case.
Yeah, you never know. So let me pull this up and show you what I meant. So here, you can see there's a DC indication. That means that the meter is in DC measurement mode. So that's what you want for this test. If you have it in AC mode, that's going to be measuring the AC voltage, the RMS value of your signal. That's going to throw you off for this test. So you want to make sure that it's in DC mode. Also, like I said, if you push this max button by accident, it will show you this little indicator at the top of the display that says max, okay? You don't want that. You want it to be just in normal mode, okay? So a lot of times when you're taking a test, you can bump one of these buttons by accident and then it can throw you all off. So you want it to be DC mode and not max, all right? So let's get back to talking about resistance here. If you want to measure a resistance, you want to put the meter into resistance measuring mode. And again, these little numbers indicate the largest value that you can measure in that particular setting. So why wouldn't I just turn this all the way up to 20 mega ohms so that I could measure any resistor I want up to 20 mega ohms? Why not just leave it there all the time?
It's not as accurate.
That's right, exactly. It's not very accurate, not precise when we're doing that. We want to get as much information about our resistance as possible. We want to get as many decimals as we can, and the higher the setting, the fewer decimal places you get. So, for instance, if I were to put this in the 200 or the 2000 kilo ohm range, in other words, 2 mega ohms, and I try to measure a resistance, I clip onto one side of the resistor, clip onto the other side of the resistor. So this tells me it's either 0 kilo ohms or 1 kilo ohm, all right? So it gives me kind of a rough estimate, but it's not very precise. So the lower I turn this, the more precision I get, the more decimals I get. So now I'm at 0.9. So if I go there, I'm 0.97. See, I'm getting more decimals each time. Now I get 0.979. So that's getting more and more precise. Now if I go down one more place, we get OL, overload, right? That means that this meter, or this resistor is too large to be measured in this section, because this meter, or this resistor is about 1 kilo ohm, and this setting on the meter only measures up to 200 ohms. So, so what you want to do is you want to go down to the lowest setting on the meter that doesn't give you an overload. That'll give you the most precise reading that you can get, okay? So you want to measure each of the resistors before you run your circuit. Now, can you just build the circuit and then measure the resistors once they're in place? No, you can't. Let's talk about why for just a second. So, let's look at an example here. So I'm going to pull this resistor out of the right-hand side of the circuit, and I'm going to measure that resistance. And I get a value of 463 ohms. Now let's put the resistor back into the circuit here and measure the resistance now.
Professor,
Yeah.
dim the light a little bit.
Oh, yeah, it's let me see if I can zoom in.
That's me.
Yeah, I wanna be able to show the circuit, and yeah, okay, so something like that. Is that all right?
Yes.
Okay, cool. So we had 463 ohms when I measured the resistor out of the circuit. Now if I measure it in the circuit, because I put it, yeah, okay. So I put it in the wrong place. So that's, if I measure it now, I'm getting 376. So why would I be getting different values there?
You've made a large parallel circuit.
That's exactly right. So what I got here in the circuit is I'm measuring the resistance between this point and that point. So that includes this resistor here, but it also includes these other two in parallel, like you said. So, so really I'm measuring the parallel resistance between these two places. So that includes more resistors. So I'm not just measuring the value of this resistor by itself anymore. I'm measuring the resistance of this whole section of my circuit. So that's why you can't measure resistances in a circuit. You need to pull the component out and measure it by itself. Okay? Does that make sense? All right, so that's how you measure the resistances. You need to do that. I highly recommend that you do that before you build your circuit, so you don't spend a lot of time building a circuit and measuring something with the wrong component in it. And then you can build the circuit, and then once you have the circuit built, you can hook it up to the power supply, and then you can measure voltages and currents. So remember, is voltage measurement a destructive measurement or a non-destructive measurement?
Non-destructive.
Non-destructive. So you can just connect. In this case, you can have the component in the circuit. In fact, you need to have the component in the circuit. You put the meter into voltage measuring mode. So that's one of these sections in the top right-hand quadrant. And then you would connect the meter to your circuit. You can just clip right onto the component like that, or you could use jumper wires and do it that way. So that's how you measure the voltages. You just connect to the 2 points where you want to measure, and you measure the voltage there. So any questions about measuring voltage? All right. And then you also need to measure the currents in your circuit. So to set up the meter for current measurement, you can put the dial into current measuring mode. So that's one of these two sections over here on the right where it says A for amps. And then you can move your, you need to move the red lead into one of the current measuring positions. So in this test, you're going to be measuring low currents, so you would put the red lead in this port where it says milliamps. Okay? The black lead always stays in the common port. The red lead would come over here to measure milliamps. Okay? So then when your meter is in current measuring mode, you can connect to your circuit. So, so in order to measure current in a circuit, what I like to do is I like to pull, so current is a destructive measurement, so that means you have to break the circuit apart at a particular point and then connect the meter to the two loose ends of your circuit. So I like to pull this lead of the resistor out of the circuit. If I'm measuring current through this resistor, I'd pull one of its leads out, and then that leaves me with two loose ends of the circuit. One loose end is really easy to see. It's the end of that resistor. The other loose end is the spot where that resistor used to connect. So that would be the hole in the breadboard where that resistor was. So I plug in a wire into that hole, and then I connect. So then the wire and the resistor are the two loose ends of that circuit. So I connect each of those loose ends to one of the leads of my meter. So I'd connect one lead to the wire, and then the other lead to my resistor, and then I would measure the current on the meter. And then when I'm done with that measurement, I put everything back the way that it started out before I go on and do anything else. Because otherwise, if I start changing too many things at the same time, I just end up throwing myself off and screwing up my circuit, and then things don't work right. Okay? So I put everything back the way that it used to be, and then I go on and make my next measurement. So, so any questions about that? Okay. All right. So that's how you make the current and voltage measurements in your circuit. If you want to measure the total resistance for your circuit, what you can do is you can disconnect the circuit from the power supply, put the meter into resistance mode, and then connect the leads of the meter to the leads, these two wires where the power supply would be connected. Again, you disconnect everything from the power supply first, and then you hook up your meter there, and then that will give you the total resistance for your circuit. Okay? Yeah?
What about measuring the total current?
So if you want to measure the total current, you would connect these leads to the power supply like they were before, and then you would break the circuit apart where the current comes into the circuit. So the current comes in from one of these two leads, so you could break the circuit apart there. So you could take that lead out, and then you would put another, you would connect that lead to one of your meter leads, and then you would connect your other meter lead to that spot where this one used to be. And then all of the current that was flowing directly into your board, that total current now has to flow through your meter and get measured, and then continue on to your board. Okay? So that's how you can measure the total current.
And you said that you still have to disconnect the power supply for current, right?
No. The power supply needs to be connected to your circuit when you measure current. Otherwise, there'd be nothing to supply the current. Same with the voltage.
Gotcha.
Yep. Yeah. So, yeah, other questions? Okay. All right, so that's how we can build this circuit. So that's what I wanted to say about the practical portion of the test, okay? So we've talked a little bit about that. So now we can go on and do a review of the semester. I know we've already taken up a bunch of time, but fortunately we've already covered a lot of the material that we've talked about during the semester. So we've already reviewed Ohm's law several times here. We've talked about Kirchhoff's laws. So we're well on our way. So one thing we haven't talked about yet is Watt's law. So let's review Watt's law. So Watt's law was all about power. And Watt's law was really more of a definition than anything else. So Watt's law said that power equals voltage times current. So you need to have voltage and current in order to have power. Remember, power is the amount of energy that's being used at a particular point. And that energy can be going towards helpful things that we like turning a motor or lighting up a light bulb. But it can also be going towards wasteful things like heat that can even be harmful or destructive for your circuit. But whether it's going towards useful or wasteful things, it's important to know what the power is. So you can calculate it like this. You can also write that this way, P, I, and V, and use that almost like Ohm's law. And then there are also two other forms of Watt's law. So power equals I squared times R, or power equals V squared divided by R. So you can use any of those formulas depending on which things you have and are trying to find. Okay? So that's Watt's law in a nutshell. Any questions about that? Yeah.
So is our multiple choice portion just going to be filled with what we did on the 3 little quizzes?
It could cover anything that we've talked about throughout the semester. Yeah. So that's Watt's law. We talked about Kirchhoff's laws. After the semester, after the midterm, we talked about capacitors and inductors. So we said that a capacitor is basically 2 plates of metal separated by a thin layer of insulation. And what was that insulation called? Anybody remember?
The dielectrode.
Yeah, the dielectric. And then there were 3 main things that determined how much capacitance a particular capacitor had. What was one of those things?
Distance between the metal plates?
Yep, exactly. So if the plates get closer together, does the capacitance go up or down? Up, exactly. So the closer the plates are, the more capacitance you have, because when the plates are closer together, those negative charges on one side have a stronger pull on the positive charges on the other side, so they are able to store more of them. So distance between the plates was one thing. What was another thing? Yep, the size of the plates, exactly. The bigger the plate was, the more area it had to store those charges. So So the size of the plates. And what was the last factor that we talked about? That's right, the dielectric material. So we said that different types of insulators led to more or less capacitance. All right, so that was a capacitor. We said that an inductor was just a coil of wire, and really any coil of wire is an inductor whether we like it or not. So that goes for the coils that are inside of electric motors, the coils that are inside of your combustion engine in your car, any electromagnets that you have, all of these things are inductors whether we like it or not. We said that if you have an inductor like this, there's a formula for inductance, and it was L equals N squared times A over little l times some constants. And where N is the number of coils, A is the area, the cross-sectional area of one of those turns, and then L is the length of that whole inductor. So, questions about that?
Are you gonna have us like? Oh, well, it's multiple choice, so it's not like we're gonna be doing any of these calculations. Or will any of the multiple choice like potentially have a calculation like this, or we have to like?
Yeah, they could.
Answer?
They could. So yeah, it could be useful to have formulas and things on your sheet. Yeah.
Can you repeat what each of the symbols are?
Yeah. So L is the inductance. N is the number of turns. A is the cross-sectional area. And then little l is the length of that coil.
When you measured in what?
So it would be whatever, I believe it would be meters. I think that the constant deals with that. Yeah. Yeah.
N was what?
N is the number of turns. Yeah. So other questions about that? Okay. And then
L was what again? Sorry.
so capital L is the inductance, and then little l is the length of the inductor. Yeah. All right. And then we also talked about diodes and transformers. So we said that a diode, the diode symbol looks like this. So this side is the anode. The other side is the cathode. And if we put a positive voltage on the anode and a negative voltage on the cathode, is that forward biased or reverse biased? Forward biased, exactly. And does the current flow or not in that condition? Yep, the current flows. And about how much voltage do we get across the diode?
0.7.
Yeah, 0.6, 0.7 volts, somewhere in there. So the voltage is approximately 0.6 to 0.7 volts, something like that. Okay? If we put the voltage in the opposite direction, so that there's a negative voltage on the anode and positive on the cathode, then is this forward biased or reverse biased? Yep, reverse, exactly. So then, does the current flow?
Nope.
No, no current. And the voltage, what is the voltage across the diode in that case?
Zero.
Yeah, the applied voltage. So it's whatever voltage we are supplying to the circuit. Okay? All right, so that's diodes very quickly. And then transformers, we said that a transformer looks like this. Basically, it's two coils of wire that are close to each other. And the main thing about transformers is that power in equals power out. So remember, power is voltage times current. So a transformer is really a device that can change the voltage and the current of an AC signal. Okay, so if you can use a transformer to take a low voltage AC signal and turn it into a high voltage, or vice versa. But since the power in equals the power out, what that means is that when the voltage goes up, the current goes down, and vice versa. So the first coil here on the transformer is called the primary. The other one is called the secondary. And the turns ratio is really what determines how much the voltage changes. So turns ratio is the number of turns on the secondary divided by the number of turns on the primary. Okay, so and we say that V out equals the turns ratio times V in. So if you have twice as many turns on the secondary, that's a turns ratio of 2, and your V out is going to be twice as big as V in. Also, I out equals I in divided by the turns ratio. So if your output voltage is twice as big as your input voltage, then your output current is going to be only half as big as your input current. Okay. Also, we said that there were some special types of transformers. So if I had a transformer symbol like this, it's got those two coils, but then it's got these two extra bars in the middle, what does that signify?
Iron core?
Yeah, an iron core transformer. Those bars symbolize a little iron form that the coils are wrapped around. And then if I have a transformer like this, and the secondary coil has an extra wire in the middle, what do we call that type of transformer? Center tap transformer, that's right. Because there's this extra wire or tap added to the center of the secondary. All right, so any questions about that? Okay. So that's a quick review of diodes and transformers. Also, we said that different diodes can have different voltages when they're forward biased. So 0.6 or 0.7 volts is typical for the silicon diodes that are most common, but LEDs have their own voltages that are based on current. So, or I'm sorry, based on color. So a red LED might be about 1.8 volts forward biased. A yellow or green LED might be closer to 2 or 3, and then when you start getting into blue and violet, they can be up to 4 or almost 5 volts. Okay, so it's based on the materials that are used in the diode. All right. So then these diodes and transformers were helpful because they could be used together in power supplies. So we talked about several different types of power supply. So we said that the basic goal of a DC power supply is to take high voltage AC electricity, like we get out of a wall, and turn it into low voltage DC electricity that we use to power our electronics. So we said that the first part of a power supply is a transformer that takes that high voltage AC and turns it into a lower voltage AC. Then the next part is a rectifier. And that takes the lower voltage AC and it gives us just a pulsating DC value that's all positive. And then after that, we could have some filtering that would smooth out our signal. And then finally, we would send that signal over to our load. Okay? So this is the simplest type of power supply. It only uses one diode in the rectifier. So what type of power supply is this? Yeah, a half-wave supply. And if we looked at the input and output, say we had an input voltage like this coming out of the transformer, the output across our load, if we didn't have the capacitor, the output would be something like this. It would go up. There'd be a little gap there because we have this voltage across the diode. So when the input was positive, the output would be positive. But when the input went negative, the output would be flat and 0 here because this diode only captures the positive half of our signal. And then we go up again, and then flat again, and so on, like that. Now, when we put in the capacitor, that capacitor smooths out the signal a bit. So the signal charges up, the capacitor charges up when the signal rises, and then capacitor slowly discharges as the signal goes down. And then it rises up again, and so forth. So we get something like this. Okay? So that would be the signal that's been smoothed out by the capacitor a little bit. Now, do bigger capacitors or smaller capacitors work better for smoothing? Bigger, because they can store up more energy, so they discharge less in between each of these charging cycles. So that's the half-wave supply. We said that the full-wave supply looked very similar, but we used a different type of transformer here. What type of transformer did we use for the full-wave supply? Center tap, exactly. So we had that center tap there. We still had our diode up here. And then our load was over here. And we had a capacitor in parallel. And then, but for the full wave, we had another diode down there, and then it came around there like that. So the full wave power supply was able to capture both the positive and the negative halves of our signal. So the output from the full wave, it went up to actually less than half of the signal from the transformer because we're using that center tap. So the unsmoothed output looked something like that. We captured both the positive and negative halves of the wave, but we got something like that. And then the discharge when you had that capacitor in there, it was smoothing things out, and it looked something like that. Okay? So that was the full wave. Power supply. So then what was the last type of power supply called?
Full wave bridge.
Yeah, the full wave bridge supply. So that was more complicated. It looked like this. We still had the transformer on the input, but now we had this bridge circuit with the 4 diodes arranged in a diamond pattern like this. And then our load was down here. So that was the full wave bridge supply, okay? And we said that this one captured the input when it was positive and negative. We had more than half of the voltage because we didn't have that center tap anymore, but we would lose 2 voltage drops because the current had to go through 2 diodes each time that it went through the circuit. So any questions about those 3 types of power supply? All right. Then we also talked a little bit about solar energy.
Excuse me?
Yes.
Why the third one doesn't have any capacitor? Because
Oh, yeah, you're right. We can have a capacitor in there to smooth that out as well. Thank you. Yeah. So then we talked a little bit about solar energy and solar cells. We said that one solar panel or one solar cell by itself doesn't give you very much voltage and current, but you could put these together to increase their voltages and currents. And these solar cells worked very much like batteries. So if you learn how to do this for a solar cell, you are really getting a double lesson because you're learning how to do it for batteries at the same time. So so we said that you could imagine a solar cell like this. You could even draw it like a battery. You could say that it provides 5 volts and 100 milliamps. And say you had a big box of these and you wanted to put them together to create a circuit that would give you, say, 10 volts and 300 milliamps. How could you put these cells together in order to get that? So yeah, so we could start putting them together in parallel. So say we've got 5 volts and 100 milliamps from each cell. If we put 3 of them together in parallel, let's see what we would get. So we could have a circuit like this, and then these 3 would be in parallel. And so we would have 100 milliamps coming out of the first one, and then we'd have 100 milliamps coming out of the second one. And so we'd have 100 milliamps coming from the left. It would join up with the 100 milliamps from this one here. So then how much current would be flowing through this wire right up there? 200, exactly. And then that would join up with another 100 milliamps from that power supply, or from that battery or solar cell. So that would give us a total of 300 milliamps up there, and then that would flow through our load and back down to the other side. So that gives us the 300 milliamps that we were looking for. But now let's look at the voltage here. So we know that each one of these cells provides 5 volts. So we could call this point down here ground, or 0 volts. And we know we have a 5 volt difference across this cell. So how much voltage does that give us up there at that point? 5 volts, exactly. And each one of these is going to be providing 5 volts. And since they're in parallel, the voltage will be the same. So we know that we got 0 volts along this wire, so we'd have 0 volts at that point. We got 5 volts all along that wire, so we'd have 5 volts up at that point. So then what voltage would we have across our load here? 5 volts. All right. So is that what we want? No, we want 10 volts. 10 volts. So we need to do something else to give us that little extra voltage. So what could we do to get up to 10 volts here? Yeah?
Put another same configuration just underneath.
Yeah.
Would add another row.
Yeah, another row, exactly. Yeah. So so we can add another row of batteries down here. So so we can go like that. And now we've got, we still have 100 milliamps flowing out of each row. So we're still getting the 300 milliamps like before, but now we got 5 volts from the top row and then also 5 volts from the bottom row. So if we start at 0 volts down here, we go up by 5 and then 5 more, that gives us 10 volts up there. So then we'd have 10 volts there and still 0 volts at the bottom. So now we've got 10 volts across our load. So now we're in business. Now we got what we want, okay? So the moral of the story is we can put batteries or solar panels together in parallel to increase their current, and we put them together in series to increase their voltage. Yeah?
Couldn't you also put those all in parallel and then use a transformer to bring up the voltage and bring down the amps?
Well, remember, transformers only work with AC signals.
Oh, okay.
And batteries and solar panels provide DC electricity. Yeah. But you're not wrong entirely. It turns out that there are things called inverters. So when you actually have a solar panel installation, it's providing AC or DC electricity, but if you want to send that electricity to a house or a building, everything in that building is expecting AC to come out. So you need to convert that DC that comes out of your panel into an AC signal. So these things called inverters do exactly that. They take a DC signal and they convert it into an AC wave. And then, yeah, you could maybe put that through a transformer. Yeah. Yeah.
What about the current, doesn't the current increase also from the 300?
Oh, so when we added another row, you mean, does that increase the current? Well, it seems like it should because we're putting in more batteries, right? But actually, it doesn't. No, because each one of these batteries supplies 100 milliamps. That means that it will put out 100 milliamps and it needs to have 100 milliamps flowing back into it. So we've got 100 milliamps flowing out up there. That means that this one also needs to have 100 milliamps flowing into this top one. Fortunately, this bottom one also supplies 100 milliamps. So it has 100 milliamps flowing out of it, and it has 100 milliamps flowing back in. So the net effect is that you just have 100 milliamps flowing through this branch of the circuit.
Oh, it doesn't increase it.
Right, it doesn't increase. So when you put more of these batteries in series, the voltage goes up, but the current stays the same. Yeah. And in parallel, the opposite is true. The current goes up, but the voltage stays the same. Yeah. So, yeah, questions about that? Okay. So those are the main things that I'm thinking of off the top of my head. Can you think of anything I'm missing? I skipped anything? All right. Yeah. All right, so then I won't keep you here any longer. I really appreciate you've been patient today, so that's been great.
Can I ask just one quick logistic question?
Sure.
To these guys? How many are planning on going into 322 next semester?
Couple people.
This
Okay.
PE class, you gotta hold up your hands. 3, 4, 5. Okay.
Yeah.
Great. And how many are music majors?
Cool.
Okay. Cool. Thank you, guys.
Awesome.
That helps us plan next semester.
Yeah. Appreciate that. Okay. So before we go, I just wanted to take a second and say that this is the first semester that we've had Stephen around with us, and I really appreciated having him here. He's been a really big help in the class, and it's been really great keeping the labs open for all of us and for all of you. And did a really great job. So I just wanted to say thank you very much to Stephen for being here. So thank you. Yeah. And also to Fred, he's been a co-teacher. He was the lead teacher for all of you for 10 classes, and Fred and I didn't really know exactly what to do about the soldering when we started the semester, because we only had the one room and more of you than could fit. So Fred jumped in there and volunteered to help out and teach you guys during that time, so that we could work that around. So, and he's just awesome. He's been really helpful and super accommodating throughout the whole semester. So I wanted to say thank you to Fred also. So yeah. And then just finally, for all of you, I just wanted to say that I've really enjoyed having you in this class all semester long. You've been great. You paid great attention. You asked fantastic questions. Keep me on my toes. I hate it when it gets boring if I'm just droning on. So you guys have been really awesome. So I just wanted to say thank you to all of you as well. So.
I think we should say the same to Jordan. He did a great job this year.
Oh, thank you. All right. So then, I won't keep you any longer. I don't think I need to take attendance on this last day, because what am I going to do? Yeah.
The possibility of a sign up some of the assignments that some of us didn't get done.
Yes, absolutely. So when we go over to lab, this will be a great chance for you to practice the practice tests that we've taken, catch up on any work, and also, definitely submit any grades that are still outstanding. I'll have the grading computer open. I'm sure Fred and Stephen will as well. So please bring up any work that you need to submit. So, yeah.